Okay, the question was, how do we measure the radius of an atom? Well, first of all, the atom has to be in a crystal, right? Okay. So if it's in a crystal, it's going to be packed together like you see here. Let's get another guy over here to help us out, because crystals typically have a minimum of 4 atoms. Oops, I want to get this back. It's easy. Okay. So we put this guy in, and that makes the 4th one. And the reason that you see it like you see it right now is because of the way the picture's made. But with this guy, we can see that we have a true crystal type structure. And let's get this together again. And what we actually have, you see, is the electron cloud, or what we call the orbital, okay, also known as a probability map, this guy. And that probability map has a line right around here. See this line? That line is 90% of where we see the electron at any given time. So if we see him 90% of the time within that line, then that means that the electrons from this atom are actually invading the space from this atom, aren't they? See, they're invading each other's space. Just like this guy has electrons traveling out here that will invade the space of this guy. So the way they pack in a crystal is the way that we get to figure out how big these things are in practice. Our probability map shows that they're bigger, but for all intent and purposes, they are not any bigger because they are now actually touching in a crystal lattice. And so looking at the probability map, which we see on another page in the textbook, that probability map will tell us that inside of that circle, 90% of the time, we will find our electrons. And what kind of orbital is this? This guy here? That's an s orbital. S orbitals have a ball shape. Okay, they're not a circle, they're a ball shape. So what I've done is hook these guys up in such a way that they will stay together, and now I can see them without the fuzzies. And this is the type of picture that you usually see in a textbook when you're seeing a crystal lattice. Okay? And so when we put these guys back on top of their orbitals, you can actually see what it would look like if you were small enough to actually see an atom. You would be measured in picometers. Pico. What was that? 1 to the minus 12? 10 to the minus 12? That's 1 trillionth. I think it's a pico, because 9 is nano. 9, that's a billion. So a picometer would be a trillionth, 1 trillionth. We're talking about really small stuff here. So that is how we measure. We get 1/2 of this distance that you're seeing that I'm measuring with this little device, and that becomes what we call the radius. Okay, and the distance between these guys is considered the diameter. Now, question number 2. The question was answered by several people, either a little bit right or just totally not even answering the question. And so I did up this little diagram here to help you understand how it works. We're talking about guys that form positive ions. Does anybody know who forms positive ions? What group of elements? Not just one column, but what big group? Alkaline metals. Who else? There's a bigger group. Metals. All metals. Okay? Now, what I'm going to do for those of you watching the video is, I hope I'm going to do, just a moment. what I'm doing in class is I'm looking at a periodic chart on the wall, and I'm using a laser pointer to point out all of the metals that are in the periodic chart. And when you look at a periodic chart and outline that group, it's almost all the elements on the chart. And the nonmetals are in the top right. I call them a den of thieves because these are the guys that take electrons, and that's the nonmetals. And the metals are the guys that lose electrons. So I call the metals a big bunch because they're most of the periodic chart, and I call them a big bunch of losers. What? These guys are down here. The actinide and lanthanide series, they're part of the metals. Yeah. Oh yeah. Yeah. That's why I outlined them. Now let's look at the diagram that I made. This is a lithium atom. Let's put the third electron in. Okay? That's lithium, the atom. Now, we measure the atom by the energy levels that are filled or partially filled. And we always measure the atom in terms of their S&P electrons. So, in lithium, for this particular guy right here, we have 3 electrons. 2 in the 1s, and where's the next one? In the 2s. Okay? So we have 3 electrons. This is lithium, the atom. Now, I'm going to draw lithium, the ion, Li, 1+, because he loses electrons, and he loses electrons because he is a metal. Now, I haven't got him right yet, do I? If he lost an electron, where does he lose it from? The valence shell. What's the valence shell? What principal energy level? 2. Okay, so that's this guy here, right? So, let's lose an electron. This doesn't exist. This circle does not exist. It's just a line that we draw. But guess what? There's no electrons out there anymore. Now what's the atom look like? Bigger or smaller? He's smaller. You bet he's smaller. Because the 2s just got cleaned out. And so if we put him back to lithium, the atom, you see he's bigger. Now, let's take this for the positive ions. Or guys that form negative ions, I'm sorry. There's fluorine, and I'm going to put an F minus, 1 minus over here. Because what fluorine does is he's in the den of thieves in the top right corner of the chart. In fact, he's the chief thief. Ooh, he's the chief thief. It rhymes. Anyway. So, here's fluorine. Let's do his electron configuration. 1s is going to have how many? 2. Okay. The 2s is going to have how many? 2. Oh, let's get this out of here. 2s is 2. And I don't have the 2s in there. Holy moly. Let's get that in there. Oh, no. There's the 2s. And the 2s has 2 electrons. 1 and 2. Okay, this is more accurate now. So the 2s has 2, and the 2p has how many? 7, right? 7. This is fluorine, the atom. Now, fluorine, the ion, does something very interesting. If lithium comes along, he can provide another electron, and he goes positive. And now fluoride, the ion, has another electron, but he doesn't have any more protons. So we tug on from 7 protons, 9 protons, I'm sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 9 protons, okay, not 10, right, because he's atomic element number 9, so he has 9 protons. So he has two that are in the 1s, 2 that are in the 2s, that's 4, and 7 out here makes 9. Get 1 from lithium, and he's got 10. When that electron gets in there, there's more shove from the electrons against each other, and there's no more tug from the middle, so it expands. And that means that now that atom just got bigger. Does that make sense? Yeah. All right, get out of here. So I've dismissed my class now, and I can actually finish this little thing up. There's one little deal that I wanted to make clear to you, that when lithium took this little electron that I'm messing with right now and gave it over to fluorine to make fluorine into fluoride. So you see fluorine became the fluoride when this guy left lithium. So another thing that happens when lithium loses that electron is that its outer shell goes away, because the only valence electron that lithium had was this guy. So his second principal energy level, lithium's second principal energy level, is no longer there. And that means he's become a much smaller atom than he was when he had that electron like this in his second principal energy level. So the negative ion gets bigger because he's actually going to swell a little bit, and the positive ion, because he lost an electron, gets a little bit smaller. And that's the way things go as ions are formed. It's always the metal reacts with the nonmetal, the metal gives the nonmetal an electron right here, and the nonmetal over here has just gotten smaller. That's how you can remember what happens when an ion is formed and how it relates to the atom that it was formed from. So just to summarize, let's look at everything nice and clean. First of all, this guy over here is our fluorine ion. He's an ion because he got this one electron from lithium, who now has no 2s sublevel and no principal energy level 2. So that's why our little lithium atom here is becoming smaller, and this fluorine atom, when it became an ion, got bigger. And this is because of all these electrons now, because there's so many of them, they're pushing each other away from each other a little more, and there's no more positive to pull them back in, because the number of protons can't change, or else we would not have fluorine. So that's why this guy is very different than the element to its right, which is neon. And neon will have the same electron configuration, but he's going to have one more proton here in the nucleus. So that's it. I hope you find this helpful.